and I am graduate student here at FES. Today the topic that I am going to present is design and analysis of near infrared laser diode. I have done this work under the kind supervision of Dr. Muhammad Usman. So for today's talk we have content here. First of all, I will overview the semiconductor materials, then the application of infrared laser diodes, and then the challenges that we have to tackle and tackle to develop the infrared laser diode. I will share some of my proposed structure of infrared laser diode along with some simulated results and then conclusion. So overview of semiconductor material. We know that semiconductor materials are those materials that have their conductivity value lies between the conductors and non-conductors. So semiconductor materials are divided into two element semiconductors and compound semiconductors. Element semiconductors are those materials that have single species elements such as carbon, silicon and germanium. And the compound semiconductors are subdivided into binary semiconductors, ternary semiconductors and quaternary semiconductors. Binary semiconductors are those materials that are composed of two elements. Ternary semiconductors are those materials that are composed of three elements, and quaternary semiconductors are composed of three elements. So next we have application of infrared laser diodes. Laser diodes are widely used in Raman spectroscopy, web space telescope, 3D depth sensing, for biomedical purposes and for security purposes and many more. Here is the interesting figure that I want to share with you guys, that how NASA unlocked the astronomers next great era. You can see on the screen that we have the picture of Eagle Nebula's pillar of creation, and the picture that is on the left is taken in the visible light, and the picture that is taken with the infrared light is have more information, that as infrared light have high energy, so it's penetrate more into the dust and other particles, so we can see more information of Eagle Nebula's pillar of creation. So in Raman spectroscopy, the infrared laser diodes are also used, that the laser light is fall on the material, so we can see its structure. So here is the comparison of Raman spectroscopy with the laser and with conventional disease diagnosis method. You can see the technology that is based on the laser is fast, have low cost, and it gives you results in the real time, and it is non-invasive, and this technology is developing day by day. So next we have working principle of infrared laser diode. As we know, the laser diodes are light emitting diodes, convert the electrical energy into light energy. There are many phenomena involved in this. First we have the photon absorption. When the hole in the valence band absorb the photon and move to the conduction band, this phenomena is known as photon absorption. The energy difference between the two bands is known as band gap energy. So next we have spontaneous recombination. In spontaneous recombination, the electron that is in the conduction band de-excite to the valence band. In this process is known as spontaneous recombination, and the energy that it emits, it is in the form of light. So next we have stimulated recombination. In stimulated recombination, this is the process that is involved in laser diodes. So the electron that is in the conduction band on the absorption of photon releases two energies in the form of light and de-excited into the valence band. This process is known as stimulated recombination. So I am working in the near infrared laser diode. You can see the infrared laser diodes, near infrared laser diodes have their wavelength from 780 nanometer to 1400 nanometer. They have high energy and short wavelength. So next we have direct and indirect band gap materials. Some materials have the direct band gap, and some materials have indirect band gap. The materials that I am using for my research is gallium arsenide that have the direct band gap of 1.42 electron volt, and other materials such as indium arsenide, indium phosphide, gallium nitride, indium nitride also have the direct band gap, where the aluminum arsenide have indirect band gap. As we know, each electron have an energy associated with it. This energy is equal to p square by 2m, where p is the momentum. If the maximum of valence band and conduction minimum of conduction band lie on the same value of momentum, then the materials have the direct band gap. And if the maximum of the valence band and conduction band minimum of the conduction band does not lie on the same value of momentum, then we have indirect band gap materials. So now we have the materials that have their energy from 1.8 electron volt to 3 electron volt lies in the visible region, but our interest is in infrared region. So the materials that have their energy less than 1.8 electron volt are in infrared region. You can see gallium arsenide, indium phosphide, indium nitride are the materials that have their energy less than 1.8 electron volt, and they lie they use in infrared laser diodes or light emitting diodes. So next we have the challenges that we have to tackle in development of infrared laser diodes. First of all, we have lattice mismatch. So some material have different one lattice mismatch, other have different. If we have to develop the layer of one material on another, so we have to minimize this lattice mismatch. So this is the first challenge that we have to tackle. Now next, you can see this is the typical structure of the laser diodes. We have N region and we have P region. In between N and P region we have active region. So we have to increase the electron injection from N region and hole injection from P region into the active region, so they can recombine and emit light. Here we have to increase their electron injection and hole injection. We also have to minimize the electron leakage, so maximum number of electron can recombine. So this is another challenge. Now I have my proposed structure. First of all, on the left hand side we have the reference device, that is LDZ1. The device is separate hydro confinement structure. This is known as SCH structure. So in this device we have many problems, that is have a large lattice mismatch, and their effective barrier height for hole is very large. So we introduce the aluminum gallium barriers in it. When we do so, so we reduce the lattice mismatch, and we increase the effective barrier height for electrons and reduce the effective barrier height for holes, so they can recombine in the active well. This is the device parameter. On a typical device have the P region, active region, and then N region. So P region we have peak lighting, that is composed of aluminum gallium arsenide, which is 1800 nanometer. And then we have a waveguide, that is also composed of aluminum gallium arsenide with the thickness of 600 nanometer. Then we have barrier, and that is P dot, and it is composed of aluminum gallium arsenide and have the thickness of 12 nanometer. And then we have quantum well, that is composed of indium gallium arsenide, which is 7.5 nanometer. And this is the N region, P region of the device, and then we have the N region of the similarly have N region of the device, that is N colliding, waveguide, and barrier. So coming to the next, these are simulation parameters such as strip width of the device is 200 micrometer, back mirror reflectivity is 0.2, and output mirror reflectivity is also 0.2, and the cavity length of the device is 600 micrometers. And we use silicon and magnesium for the N and P doping. So next I will share simulated results. So first of all, we have internal quantum efficiency versus current density. You can see the where the quantum internal quantum efficiency is increased to 82%, and that is of red line or red graph red line. You can see that the droop of the device is also decreased, and the efficiency droop is decreased by 31%. Next we have the power versus current density graph. The output power of the device is 65 milliwatt at the current density rate of 12 multiplied by 10 raised to power 4 ampere per centimeter square. the power of the device is increased, and also the threshold of the device is lowered. And that you can see, we observed that the threshold of our reference device is 1132.8 ampere per centimeter square, where the reference proposed device is 637 ampere per centimeter square. Now next we have refractive index profile. The figure that is at the left is of reference device, and the figure that is at the right is of our proposed device. The refractive index of the device is decreased to 3.2, and also the model field intensity of the device is increased from 1.3 to 1.8, and the total model field intensity of the device is increased by 28% as compared to the reference device, which is LDZ1. And also you can see that we get the refractive index profile a sharp sharp curve, so we can see the intense light is now generating. Next we have the electron and hole flux. As we know that the electron from the N side come into the active region, and hole from the P side come into the active region, and they recombine and emit light. So we have to maximize the electron into the active region. The area that is in the dotted line is active region. So you can see for the reference device, and that is black curve, have the high electron flux. This means the less number of electron are coming into the active region. And for the proposed device, the red curve, you can see at the right, and the electron flux is minimized, so the large number of electron are coming into the active region, and the electron leakage is decreased to almost 5.4%, and the electron leakage of LDZ2 is reduced by 44.2%, where the whole we have to increase the whole into the active region so they can recombine. You can see the whole in the active the whole flux the black curve, the whole flux have the less value, that is for the reference device, and for proposed device, and the red curve have the maximum number of holes coming into the active region. Next we have stimulated emission. So both the LDZ1 and LDZ2 are emitting in the infrared region, but there is a small shift in their wavelength from 840 to the 860 nanometer. This means that because of introducing the barrier to the structure. So the stimulated emission is increased for the proposed device. This means the more light or more carriers are recombinate in the active region. So in conclusion, we have observed our device on different doping concentrations. We believe that the doping concentration, that is 5 multiplied by 10 raised to power 19, is perfect for doping concentration for barriers. It's almost all parameters such as threshold, power, refractive index, stimulated emission is good with this doping in the barrier. So these are some amazing people that helped me throughout in this research work. I would like to thank them. Last but not the least, thank to you guys for coming here. Thank you.